I just start recording. Last time we began the analysis of one of the, let's say, of the core, we can say, of what is a thermal rocket, because I would like to recall that the thermal rocket is based on the conversion of internal energy to kinetic energy, and this is done for different devices that go from the, let's say, cold gas thruster to electrothermal thruster up to the large engines that we use in launchers. So but applications for attitude control and main thrust that is used for orbital maneuvers or for launcher stages. So in these thermal rockets, this conversion of energy occurs in a device which is referred to as nozzle, and this nozzle is can be analyzed in a step-by-step. We will analyze different properties starting from the ideal case, and we made a number of assumptions that allow us to talk of this ideal nozzle. And the study of ideal nozzles, that means that we are considering a homogeneous gas expanding the nozzle without any role of friction, of heat addition, of mass addition, that we consider a chronically perfect gas. We have no solid particles inside or condensed particles in general. We have no reactions. So it is an ideal vision of an ideal image of this component that is going to be studied to identify the main dependencies of the that also draw the design of this part of the rocket. So what we have seen last time, let me share the screen. Sorry, one moment. Yes. So what we have seen last time is that we have found an expression for the exhaust velocity because, let's say, first of all, we are considering the goal of our rocket to generate a thrust, and we recall that for in the one-dimensional assumption of the flow, we found at the beginning of the course that we have this relation defining So can you hear and see me?
Sì, professore.
Grazie. So I was saying that we went back to this expression for the thrust, which is our driver. We are going to realize thrust through our rocket, and we found that this thrust is related to the mass flow rate, the exit velocity, and the exit pressure, and to this term, which is also depending on the environment, atmospheric pressure, and to the exit area. So we are assuming here that we have a device with a given exit cross-section E, where we have a uniform velocity, 1d velocity, and we have a given cross-sectional area. We have an environment with a given pressure here, and this velocity, this area, and the local density and pressure, which are properties of the flow exiting our device, will allow us also to determine the exit mass flow rate. We have also seen that if this is our goal, the quality of this goal is measured by the specific impulse, which is just F over dot M, that can be expressed as UE plus PE minus PA over dot M by AE. So in general, we have to study to analyze this expression and to see how to improve the quality of the generation of thrust. We should analyze these different quantities that play a role, dot M, UE, PE, PA, and AE. We see that from the expression of specific impulse that for sure one important role is played by the exit velocity. So we started our analysis by this quantity. And what we have seen is that exploiting the energy balance in terms of enthalpy, we can express this velocity as square root of 2 gamma over gamma minus 1 r T0, 1 minus PE over P0, gamma minus 1 over gamma. So with this expression, we made already some consideration. Because we see a clear dependence on the initial energy content here, and we will talk about this later, and another term that, except for the dependency on gamma, we see this other part that tell us that we should prefer low values of P over P0, because we have seen this is the inverse P0 over PE, that we have a behavior more or less like this of UE over square root of RT0. This is what we were seeing at the end of last class. So what this is let's say this is a log scale that tells us that this part is rather limited, and we see that a quick change is obtained by, let's say, what seems small here, but means that we have a large change of this ratio. Actually, we have also said that 50 could be a first level that allows us to increase this exhaust speed as much as possible. Why we would like to have this exhaust speed high? Because we have seen that specific impulse is related to this exhaust velocity, and so this is why we are aiming to get this velocity high. We have also identified that we have a maximum when this term goes to 0. That means that we convert all the energy available in kinetic energy, and this maximum is obviously this one. So at this point, we also see that that to have, starting from this relation, as entropic relation between total pressure and local pressure, we also record that we have that if here we plot this ratio as a function of the Mach number, we see also that we have something like this. As a strong decrease for Mach number larger than 1. So if we have to move towards values of P0 over PE large, that means P over P0 small, means that we have to move towards high Mach numbers. And so we can also introduce further final comment that from here, from this expression, we see also that U maximum over square root of RT0 tends to is obtained when the maximum value is equal to square root of 2 gamma over gamma minus 1, and this is a quantity dependent on gamma, and in practice it is higher the smaller is this gamma. This gamma is a property of our gas at this moment. And this is square root 2 gamma over gamma minus 1 that tell us that here, if you start from 1.1 up to 1.67, that is the maximum range that we can cover for this gamma. And we'll have values between 4.7 here and 2.2 here with let's say 3.5 when gamma is 1.2, but you can easily see this plot. So at this point, we know that we have to obtain this P0 over P as high as possible, and that we need Mach number that are also high. We know that by assumption that we made in the study of this ideal nozzle, that the inlet velocity is more. So we know that we start from subsonic Mach number and we move towards supersonic one. We know that there is a way to do this, but let's start first from our, or we start again from our inlet condition. So we have a device where we start with a Mach number less than 1, and we have to accelerate it. So we know that we need a converging channel. Something like this. Let's say this is a converging channel. This is an enclosure where we have given values of P0, T0, H0, and so on. We have no velocity here. This is small enough that the amount of gas exiting from this enclosure that we can consider zero velocity inside. And we can identify here our inlet and here our exit position for our one-dimensional analysis through this converging channel. So first of all, we have to recall what is the driver for the existence of a flow here. So we know that we have an environment with a given pressure PA, and different conditions may occur. The first one that we can consider as a reference, or a first reference, is the case where we have the same pressure inside and outside. So P0 is equal to PA. What happens in this case? It's obvious. We have no flow. There is no reason for the flow to exit the enclosure because we have the same pressure. So pressure, the pressure difference, is the driver that allows us to, let's say, generate a motion. There is a force because of the pressure difference that accelerate our fluid. And so we can expect that something occurs, or there is some dependence on the difference between these two pressures, P0 and PA. So we can imagine that if this PA is slightly smaller than P0, there will be fluid motion. So we generate a flow within our converging channel, but probably the velocity will not be so high. It will be a small amount of flow rate. This is, let's say, we can say also based on our understanding or basic understanding. So, but we have also obtained some relation so that we can say that if here we are at the external environment, we have a given pressure, we can check the relations that we consider valid in this isentropic flow through this converging channel, and we can exploit the relation and see what will be the velocity here. And in fact, we can easily write that in this case we have that PA, we can assume PA equal to PE equal to PA, and so we have that P0 over PE is what you have already written before. As this expression, and so we can easily extract Mach number from here. It's 1 over delta P0 over PE gamma minus 1 over gamma minus 1. So we see that we have in general this relation that allows us to express the Mach number at the exit section, and so through this relation also the exit velocity that we have written here, because if we know the ratio P over P0, we also know the exit velocity. Good. We also say that here actually we have PE equal to PA, so if we go to the expression of thrust, we see that we have only the impulsive part remaining, so we have no pressure thrust because we have, as we called it, adapted nozzle, and so the expression is quite easy, and this exhaust velocity is also equal to the specific impulse. So we have that here, F UE, and so it's a very special case. But
Prof, scusi, posso fare una domanda? Nel grafico P0 su PE in funzione dei Mach, è P0 su PE o PE su P0?
sì, P su P0 che diminuisce con numero di Mach, certo.
Grazie.
Prego. Grazie a lei. So we were now saying that at this point we have an expression for the exhaust velocity, but we still have to do some consideration about the geometry, and we will see this analyzing also the behavior of the other quantity that we have here, which is dot m, the mass flow rate. So let's look to this expression, to the expression that we can obtain for this mass flow rate. Dot m is equal to rho e ue ae, and we can exploit the properties of our isentropic flow to make appear in this expression the constant value that we have in our enclosure, and that which are written with the subscript 0, right? So the total values. And for the density, I will consider, for instance, this in this way, and rho e over rho 0 by rho 0. And for the velocity, we use the Mach number and the speed of sound. And we also divide and multiply by a0. And finally, we have the exit area. So here we can express everything in terms of the Mach number and then of the pressure ratio, because we have this relation between the pressure ratio and the Mach number. So actually we can write here rho e over rho 0 is Pe over P0 to 1 over gamma, and AE over A0 is PE over P0. The temperature will be gamma minus 1 over gamma, and the speed of sound is square root of temperature, so it's gamma minus 1 over 2 gamma. Then we have here the expression for the Mach number, and I can make the substitution in this expression. Let's leave it in this way, and we have that dot m is equal to, I group the quantity which are, let's say, independent of the pressure ratio, and then I have P over P0 to 1 over gamma. Then I have the Mach number, which is 2 over gamma minus 1, which is this delta, was 1 over delta, and P0 over PE, gamma minus 1 over gamma minus 1. This is 1/2. And here we have the last term, which is AE over A0, and so P0 gamma minus 1 over 2 gamma. So we can put everything, all these terms, under square root, and because we have 1/2 here, we have 1/2 here, and so here will be twice the value divided by 2 gamma, and it becomes rho 0 A0e square root of 2 over gamma minus 1. Then we see here this will be P over P0 2 over gamma, and here we have to consider that you are multiplying P0 over P to gamma minus 1 over gamma by its inverse, the same power, so this is 1. And then we have just this inverse, considering multiplication of this by the two terms that are within square brackets here. So you can easily obtain that Pe over P0 here is to the power 2 over gamma. And here we, within the square brackets, we have 1 minus Pe over P0 gamma minus 1 over gamma. And this should be okay. So we notice that in this expression we have, let's say, a constant part for a given exit area. So we go back to this drawing. We have a given exit area here. We have just this shape. And for a given exit area and reservoir condition, we have this expression that depends on, we were saying that it's an adapter nozzle, so it depends on the ratio between the ambient and total pressure. So let's look what happens for varying these quantities, that is the exit pressure. If we consider now just, so it could be here, for instance, dot m over rho 0, A0, AE, and also square root of 2 over gamma minus 1. So we see the behavior of this term under square root. And what we see is that, of course, if Pe is equal to P0, so if you have the atmospheric pressure equal to the reservoir, of course, we have that here 1 minus 1 is 0. Okay, this is when this is 1. If we go increasing this value, that means we decrease the value of ambient pressure so that we have a flow from the reservoir towards the ambient. That is what we are interested in, of course. We see that this mass flow rate is looking to, if you plot this expression, you see that we are going to increase this mass flow rate. But you also see, looking into this expression, that if we go towards values so high of P0 over Pe, that means this P over P0 tends to 0, that of course is equivalent to say P0 over Pe tends to infinity. So if you are decreasing, once we decrease sufficiently the ambient pressure compared to the reservoir pressure, we see that we have again, here we have a 0, so this becomes, terms in square brackets becomes 1, whereas this term goes to 0. So we have to imagine that here we are also going towards 0. And this is a positive function, so we can expect that somewhere we will reach maximum value. So what happens here? Because we can now, if mathematically we have that this line continues, we pass the maximum and we go towards 0 at infinity. So from, let's say, our schematic here, from the point of view of this, what happens is that we are decreasing ambient pressure, and in the first branch we have that mass flow rate is increasing, and at a given point we reach a condition such that if we further decrease the ambient pressure, we have no longer increase of mass flow rate. But this doesn't mean that we move on this other branch of the line. We have reached the maximum, and what happens is that if we further decrease ambient pressure, we are not going to reduce mass flow rate. Actually, what is happening is that we have reached the choking condition. So let us let's say this. We are considering a converging channel with this expression that allow us to identify the mass flow rate based on the exit area, and what we see is that we reach maximum mass flow rate. This expression is also referred to as the equation of the de Saint-Venant. And it's often written instead of, and we will do it usually, instead of putting here rho 0 at 0, we can express this in terms of pressure and temperature. Rho 0 at 0 is P over RT. This is the square root of gamma RT. So what happens is that you have gamma over square root of RT0, and so at the end you have that dot M is equal to P0 AE square root over of 2 gamma over gamma minus 1 over RT0 P0 2 over gamma 1 minus P0 gamma minus 1 gamma. So this is the Saint-Venant equation, the de Saint-Venant equation, which is plotted in this way, where we found, let's say, a maximum value. And if we further decrease pressure, ambient pressure, we remain, if I write this PA, what happens is that we reach a maximum mass flow rate for a given value of the ambient pressure, and so we once we have reached this maximum, we cannot go further. It's interesting to identify which are the conditions for this maximum, which are the choking condition, of course, and we can identify this by just finding this maximum through the derivative of the terms which depend on pressure. We can make the, let's say, if we look for the dot M over the PE over P0, and we look for this quantity, for instance, greater than 0, we find that we have to make the derivative, so this will be 2 over gamma. I look only on these two terms, 2 over gamma PE over P0, 2 over gamma minus 1. Minus 1, I write this in this way. That multiplies 1 minus PE over P0, gamma minus 1 over gamma. I'm just doing the derivative. And so the second term will be, let's leave the room for the sign, but it will be PE over P0, 2 over gamma, and then the derivative of this term, that will be only the second one, so we have a minus, and we have PE over P0, gamma minus 1 over gamma, minus 1, and here the multiplying factor, that is the exponent of the power as known for the derivatives. So we have this condition. Written in this way, I can simplify for sure this and this. also this gamma. And what is left? We have 2 minus 2 PE over P0 gamma minus 1 over gamma, and then here minus gamma minus 1 PE over P0 gamma minus 1 over gamma. So I can put together terms with P over P0. It will be have minus 2 minus gamma plus 1, so it would be minus 1 minus gamma. And I bring this on the right hand side, so that 2 must be greater than gamma plus 1 or P over P0 gamma minus 1 over gamma must be less than 2 over gamma plus 1. And this is exactly what happens when we are at sonic condition. In fact, you recall that PE over P0, third time at least that we are writing this today, in general is 1 plus gamma minus 1 half m squared to the power minus gamma over gamma minus 1. And so we see that here, when Mach is equal to 1, we have 2 over gamma plus 1. So if we can replace it here and have also this expression in terms of the Mach number, and we see that we have here 1 over 1 plus gamma minus 1 half m squared must be less than 2 over gamma plus 1. Is it correct? P over P0 is 1 over 1 plus delta squared, and yes, so it becomes that 2 plus gamma minus 1 m squared must be, this is on the right hand side, must be greater than gamma plus 1 or gamma minus 1 m squared must be greater than gamma minus 1. So this is the condition for the derivative that I made with respect to P over P0 must be positive. So if we go back to this concept, of course, this is P0 over P, so we are moving in this direction, and we see that we have an increase of the Mach number with P over P0 when we are in the supersonic branch. whereas we have a decrease when we are in a subsonic branch. A decrease of Mach number for increase in P over P0. Of course, if we look towards the dependency of P0 over P, is the opposite, is the inverse behavior. So we see that we have that our mass flow rate is increasing with P over P0 when M is less than 1. Then, so dot M increases with P0 over P increasing, provided that we have that M is less than 1. Then we reach at M equal to 1, you have a maximum. So this corresponds also to our understanding that at this point it's also true that we have no longer the possibility to inform in a way what is ahead of our exit section of further decrease of the ambient pressure. So this is what happens when we have choking. We have no longer information going from let's say downstream towards the upstream flow condition. So we reach this maximum, and it actually is important also to understand if this is the case when for our application. And in fact, what we have to say here is that this happens when the ambient pressure is less than this critical value here, which is the one to which corresponds Mach equal to 1. That can be expressed as P0 over PE is gamma plus 1/2 to gamma over gamma minus 1. So this is the critical value. So if PA is less of this critical, it means that we have choking, choked flow. And what is this pressure? We have just to replace here gamma in this relation to see that, of course, we can see this in terms of P0 over P star or by the inverse. And if you look here to the behavior, as a function of gamma, we see a decreasing value of this critical pressure with P0, but of the critical pressure ratio with gamma, but you see also that we can identify the range of this quantity. And this is not so wide. And in fact, we have values here, for instance, 0.53 at 1.1 and at 1.4. Sorry, 0.58 here, sorry. And I have 0.53 is actually here at gamma 1.4. So the range is rather small, and we can say between 0.5 and 0.6 roughly, or by the inverse, we can consider between 1.7 and 2 that tell us what? That if we have this converging channel and we have a pressure inside the container, the enclosure, which is more than twice the ambient pressure, we will have choked flow. And this is said independently of the fact that we have a converging channel or just a hole in the tank. So if we have in the container, if we have tank of gas here, and we just make a hole, and we are in vacuum, there will be chocolate flow through this hole. We know how much mass flow rate, easily how much mass flow rate there will be through this hole. And the same is independent of the shape of the hole. Just the fact that we have this pressure difference tell us that we cannot, if this pressure difference is greater than 2, we will have chocolate flow. And so the mass flow rate will not be different if the pressure is 100 times lower than the enclosure pressure or 50 or anything else. So we can stop here for 10 minutes and we will resume at 1:10. So let's resume and see what is this maximum mass flow rate that we can extract from our container. This mass flow rate can be obtained just considering that our PE is equal to the critical one, and so substituting within the Summerland equation the expression P over P0 equal to 2 over gamma plus 1 to gamma over gamma minus 1. Let's do it. And we have that dot M is equal to P0 AE square root of 2 gamma minus 1 over RT0. And then here I have to replace this, it was to the power 2 over gamma, and it becomes now 2 over gamma plus 1. That here was 2 over gamma, becomes 2 over gamma minus 1, because of this gamma here. And then we have square brackets 1, 2 over gamma plus 1, which is gamma over gamma minus 1, and gamma minus 1 over gamma. That cancels. So it becomes simple. The term in square brackets is 1 minus 2 over gamma plus 1. That becomes the following. Then we have here, it becomes square root RT0, and then 2 gamma minus 1, here gamma minus 1 over gamma plus 1, and this term here, sorry, gamma minus 1. Very good, this simplifies, and you can recognize here further gamma plus 1 half. So if I put all 2 over gamma plus 1 on a single power, we have that it should be 1 plus 2 over gamma minus 1. So it becomes gamma minus 1 plus 2 is gamma plus 1 over gamma minus 1. So this was the power at which we find here the this 2 gamma plus 1 and this 2 gamma plus 1 here. So we can, but you see, we can go back and express this as that multiplies square root of gamma and 2 gamma plus 1 to the power gamma plus 1 over gamma minus 1. So we have that our mass flow rate is obtained, maximum mass flow rate is a function of the exit area, the total pressure, the total temperature, and of gamma. Practice this, we will find often this function of gamma, which for the application of our interest changes only of small amount for the variation of gamma that we have to consider. So it's more or less constant. And this gamma, this function of gamma, we will call this as capital gamma, and this referred to as the function of band and Kerkhove. And has a little variation, little change in our range of gamma. This is 0.72, but this is related to the high values of gamma that can be of interest for cold gases. When I put 1.6 here on this right, as maximum value of gamma, I'm referring to the fact that we are talking about thermal rockets, and within thermal rockets we have also rockets operating with monatomic gases. For instance, some cold gas, in principle, using xenon, for instance. And in this case, the isentropic exponent for monatomic gases is 1.667. Is 5/3. So we see that actually if we consider the range of chemical propulsion, this gamma is within 0.64 and 0.67. So you see there are limited changes. So summarizing, we have that for the flow that is exhausted through our convergent nozzle, we can have two possible situations. First one, that PA is greater than the critical pressure, which is 2 over gamma plus 1, gamma over gamma minus 1, P0. In this case, we have that mass flow rate is increasing with decreasing ambient pressure and is the function expressed by the equation of the Saint-Venant. In case we have the other possibility is that PA is less than P star, which is of course the same, and in this case we can express mass flow rate by this relation that we have just seen. So we have a maximum mass flow rate which does not depend on the ambient pressure. So an interesting point here is that we have realized the choking conditions. So we know that reducing this pressure, we have this choking condition. Then we can say, okay, we have reached the maximum flow rate and also velocity is good, and we stop here. But we have noticed that we need high pressure ratios, and the choking condition only allow us to reach something like 2, whereas we were saying at the beginning of today's class, we were saying that perhaps 50 could be the minimum value that starts to be interesting in terms of expansion ratio to have good specific impulse to have high exhaust velocity. So but we know that if the ambient pressure is significantly lower than the total pressure, we reach easily this choking condition, and we know what we have to do now once we have reached the choking condition to further increase speed. We have to add to that hole a diverging channel, and in this way we exploit the choking condition. We exploit the fact that changing the sign of the area variation, we pass through the condition where lambda is equal to 0, and so that we can switch from at m equal to 1, and so we can switch from subsonic to supersonic flow. So with a converging diverging channel, we can consider that the cases with PE over P0, which are less, PE over P0, which are less than P star over P0. Converging diverging channel. So to pass to this kind of nozzles that are called de Laval nozzle. Passing to this de Laval nozzle, we can exploit now the same the Saint-Venant equation, but reading it in a different way. We were seeing it in terms of the effect of ambient pressure on the mass flow rate. Now we would like to use it once we know which is mass flow rate, because we know that if we have a converging diverging nozzle and sufficiently low ambient pressure, we have choking conditions, so we know what is the mass flow rate that in this case will be related to the minimum cross-sectional area that would be referred to as the throat area. So AT is the throat area, and dot M will be gamma P0 AT over square root RT0. So the expression of Desarmes-Venant includes, says that dot M is P0 AE and then so on. So square root of. Before we have considered that this AE is constant, or better is the exit area, and we see the effect of ambient pressure. Now we can consider that this mass flow rate is the one governed by the choking condition, and we see what is the relation on the right hand side between this AE and the pressure ratio P over P0, which appears here in this expression. We have 2 over gamma, and then we have square. Okay, I don't write everything at the moment. I will write it again soon. So if we look to this, and now we plot again we have here, and we can write dot M square root RT0 over P0 AE. So in this case, if I plot this quantity here, in practice, I'm showing the evolution, and this as a function of P over P0 now. I'm seeing the evolution of 1 over AE, because all the other quantities are fixed in this case. That M is the critical one, T0 and P0 are the conditions that we have at the enclosure. So we see here we have something that goes from again 0 up to 0. Because this was the dependency that you have seen here with the maximum. And of course, we have that here the pressure is closer to the total one. So here we have Mach number less than 1, and here we have Mach number greater than 1. So here we can exploit from this plot. We can see that if we move towards lower values of PE over P0, and we like to reach these lower pressures, we will have some area which is here as a lower inverse, so it's greater. And this is identified by this value here in this graph. Yes. So now let's consider let's exploit this relation here within the Desarmes-Venant expression. We have that gamma P0 AT over square root of RT0 is equal to P0 AE square root of 2 gamma over gamma minus 1 over RT0 P E over P0, 2 over gamma, 1 minus PE over P0, gamma minus 1 over gamma. So with this, we see that what is represented in this plot just shown can be identified by an equation that, simplifying here, this one, also P0, allows us to express the ratio of the area, of the exit area to the throat area, which is needed to obtain a given value of P over P0. So this is nothing new. This is the same law that you have already seen looking to the area, the case with area change of the 1D flow, isentropic flow with area change, except that instead of expressing it in terms of the Mach number, it is expressed in terms of the ratio P over P0. We often take this quantity, we call again another epsilon. Here the epsilon means the area ratio, because this is an important quantity in our design of the rocket nozzle, of the thermal rocket nozzle. Another important quantity is, of course, the ratio P0 over PE. These are both ratios greater than 1 that we can call as pressure ratio. And this is the area ratio. Consider that saying expansion ratio is used for both pressure ratio and area ratio. Despite it's more correct to call expansion ratio is more appropriate when you are talking of pressure ratio. This is also called expansion ratio. So what we do with this expression, what we can say that we can try to identify how our exhaust velocity, because we can go back to our UE, that was the reason why we are moving towards this supersonic flow, and we can express our UE as a function of the velocity we have at throat. That will be actually of course, also the critical speed of sound, and this will be 2 gamma over gamma minus 1 RT0, 1 minus PE P0. This was the expression of UE, and this is the expression of UT, where the difference is, of course, the pressure you have here. And so you can simplify. And here we can replace, we have seen before that this square brackets is also equal to 2 over gamma plus 1. No, there's something wrong. This term in brackets is is 1 minus 2 over gamma plus 1. So is gamma plus 1, and on numerator we have gamma minus 1. So at the end, we have here gamma plus 1 over gamma minus 1, 1 minus Pe over P0. In this way. So we see this is the increment that we can obtain in terms of exospeed with respect to the only converging channel when we consider the diverging portion, and in particular this will depend, of course, on how lower than the critical will be the exit pressure. And we can plot, let's make different lines on this plane where we have log scales for here on the abscissa we have P0 over PE, for instance from 10 to 500, and on the ordinates we have, this is 1, let's say 3 and 10, and this group of lines refer to the ratio of epsilon, sorry, this is related to epsilon, and for varying gamma. So we have also here varying gamma, and this is UV over UT. So these three lines are related to three different values of gamma for UV over UT, and these three lines are related to epsilon A over AT. So we see that for varying this pressure ratio, for increasing pressure ratio, we have an increase of UV over UT, and exactly as you have seen for the only UE, we have something that is trying to reach an asymptotic value that in this case will be square root of gamma plus 1 over gamma minus 1. Whereas this area ratio is always increasing with this pressure ratio. So the comment here is the existence of a diverging part of the nozzle allow us to increase a factor up to 2 or 3 times the exospeed. To do that, we need rather high values of this AE over AT, which is our area ratio. We can also see, if we make this plot at a larger scale, we have that, let's say we start from 300 this time and we go up to 10,000, making things exaggerate. We see that this is almost flat. We are close to the asymptotic value, whereas we see that the area ratio continues to increase. So we can easily understand that that from a given point on, possibly is not so interesting to increase the area ratio as we have bigger nozzles heavier without a corresponding interesting increase of the exhaust velocity. And so this is, of course, something quite important that allows us to understand that it's not always true that we like to go to very high expansion ratio, but this will be also discussed in details later. Let's go now to make further consideration on the behavior of converging diverging nozzles. It can be useful to make a step back and make some further consideration on what happens to a choked flow when we have lower value of pressure in the ambient. So we know that we have, for instance, let's make it simple, we have something that ends in this way. So our throat area is more or less constant. So we have uniform flow here, and it's simpler. And we have here a given pressure. We have M equal to 1 and P equal to this P star, the critical pressure. Whereas we have here PA less than P star. What happens here? We have a given pressure, we have a sonic Mach number, and the flow has to expand to reach the ambient pressure. And so there will be, if you go back to your gas dynamic curves, you know that we have a characteristic line that is Mach line, which is perpendicular to the flow direction if Mach number is equal to 1. And then you will have to expand, and you can expand here through this corner up to reach the ambient pressure. You can imagine something like this, a fictitious world, such that you have an Brandmeier expansion here that turns the flow in this direction and allow the flow, the supersonic flow, the sonic, the transonic to supersonic flow to expand and reach the ambient value. And these, of course, symmetrically occur on the other side. So what happens here is that the flow changes pressure going towards what it has to do, that is reaching to the ambient pressure through an expansion that occurs outside of our nozzle, because it was a sonic nozzle here, let's say a subsonic up to sonic choked nozzle. So what happens here is that in a planar case, this would be is easier to be discussed, but we have to consider also the axisymmetric shape that usually we are interested in. But also in the planar case, what we can see is that here we have pressure waves coming from this side and also from this other side. So they interact with each other such that we actually signal, for instance, here, linearized for simplification, is an expansion signal that say here that we should decrease the pressure, but pressure is fixed outside. So actually this expansion wave should be balanced by a compression wave. And to make this compression wave, we have to turn on the other opposite direction. So what happens here is that actually we don't have just this diverging flow, but it starts diverging, then it turns back, it generates, it's a supersonic flow, compression will generate a shock that form a Mach disk. Here, this is a normal shock. And so there will be a tripod point with a shock reflection. And then we have that the jet here will be at a given angle, will reach again this shock, and now further expansion will occur, generating the well-known diamond shape that we see in supersonic jets. And this occurs also if you are just considering m equal to 1 here. So you see, this is the case where the E is not equal to PA. Actually, we should have expanded more to reach the ambient condition. So we expanded less than we could, and so we call this jet, in this case, it's just a converging nozzle, is in underexpanded condition. So if the ambient pressure is less than the exit pressure, we could have expanded more. So we are in an underexpanded condition. This is a case of non-adapted nozzle. So we have also the pressure term to be considered in the thrust expression. Whereas the choked nozzle is also called the saturated nozzle. So in case, let's now go back to our converging diverging nozzle. And we'd like to see, to make a similar discussion, this can be considered as the final part of the former discussion we have done for the converging nozzle. When we were considering, we started from the case that we have PA is equal to P0, we have no flow, then we decrease pressure and we saturate. And this part, this short discussion here, is what happens once we saturate, when we go to further lower ambient pressure value. There will be something outside that will rearrange the flow towards the atmospheric condition. But it's something happening outside, so it does not affect. You recall that what's important are the forces acting inside on the walls that characterize our nozzle. So what happens outside has not direct effect on the resulting thrust inside. So let's now consider, try to follow the same evolution for a converging diverging nozzle. So we consider something like this, a simple one. Here we have a symmetry axis that we can consider this planar or axisymmetric. And we would like to analyze the behavior of P over P0 as a function of our x along the axis. We have to here well-identified position for the throat, an inlet cross-section, and an outlet cross-section. So, of course, we have a first condition of this, the no flow condition. Here we can identify a value which is 1. No flow condition is along this dashed line. Then, if we consider, for instance, this pressure value here at the exit, so we will have pressure slightly lower than the total pressure. If this area here, for instance, are the same, I will have slow flow, subsonic flow that for the same area will be at the same value of P over P0. And then we have that going from here, from the initial position to the throat, there will be a converging channel where we have a decrease of pressure. Let's put it this way. Perhaps it's already too much, but okay, we can consider different cases. Corresponding to different value of ambient pressure. I'm changing here on this right-hand side of this figure. I'm considering the solution corresponding to different value of ambient pressure. So you see, these are two possible conditions with all only subsonic flow. So we know how to manage it because we know the relation between area ratio and Mach number, or area ratio and pressure ratio, as we have seen before. But we have to keep in mind that at this point we have also a special line that is the critical pressure. We say that is more or less 1/2 of the total pressure. So what happens? You see that we will have a given point, a given value of ambient pressure that will allow us to reach the critical value. And you see that here, in this red line, you see that actually we just reached this critical value of throat, but we went back, remaining in subsonic branch, to the ambient pressure, which is higher than the critical one. So you see that we reach these conditions for even if the ambient pressure here is not is higher than critical one. So we can saturate the nozzle, the converging diverging nozzle, even if, because of this converging diverging shape, even if the ambient pressure is higher than the critical one. If it were only convergent, we should look at this abscissa, and so the ambient pressure has to become equal to critical to reach saturated conditions. We can also identify, then we can continue to decrease our ambient pressure. So the first thing that we can imagine is that something occurs outside of the nozzle. Because the only other thing that we can imagine is that for the isentropic solutions that we can obtain for this converging diverging nozzle, we have a second solution, which is this one. We recall what we analyzed with lambda. We can switch to the supersonic branch and reach this other special value of ambient pressure that is referred as P sup here, supersonic value, that corresponds to see that we continue to decrease pressure now. That means we are increasing velocity, we are increasing Mach number, and we are decreasing pressure. So if we imagine that you are varying the ambient pressure, what we know is that for this regime here, for each value of ambient pressure, there is a corresponding value of pressure evolution along the converging diverging nozzle. This is also true if we consider pressure lower than the minimum pressure here, this P scoop. That means that we have the supersonic flow within the diverging part of the channel, and we have here a supersonic jet that, if we consider pressures which are lower than this one, is the same that we have seen for the chocolate nozzle, chocolate converging channel, when we have pressure lower than the critical one. So here we have something which tell us that the nozzle is underexpanded, and there will occur something outside the nozzle that will adjust the pressure with the ambient. So the question mark is related to what happens here when the ambient pressure is between these two values. So the first thing that we can say is that there will be some something that will occur outside to adjust the flow to the ambient pressure, because inside we have just these two possible solutions. But at this point we don't even know which of the two solutions will be followed by the flow. Will it be all supersonic in the diverging section and then adjust outside with some compression rather than expansion? Or will it be subsonic and then will adjust in some way outside the nozzle? What we can say is that this should be the case as far as we consider that there is no chance to have that we have only isentropic flows. These are the solutions. But in the real world, we have to consider that possible non-isentropic solution may occur. And if non-isentropic solution means that there can be some entropy increase due to something like, for instance, shocks that occur in within the nozzle. So entropy increase is related to pressure, total pressure decrease, and if we consider, when we have obtained the area ratio from the Sandvinan equation, we have simplified total pressure. If we now don't make this simplification, we can write this ratio by making explicit the possible difference between the total pressure at throat and at the exit. And this was the expression that you have got for the area ratio in the isentropic case. So this could be related to the isentropic branch after a change of total pressure. So the new isentropic flow will be based on this P0E, and this will be the one which is related to the exit conditions. So we will continue tomorrow to analyze this case, which is the case where the pressure is between the subsonic and supersonic isentropic solution, and that we will show that if we consider a lower total pressure, we have to shift down these lines, and so we can have this position could correspond to this isentropic solution in the divergence section that, of course, implies that we should move from this supersonic branch to this one. And this will be compared to the normal shock expression that you have obtained in the gas dynamic or compressible flow courses. So we can stop here.